Okay, welcome to class. So take a second and I want you to dissolve some sodium acetate into water. So what I want you to do is on your paper, draw these ions and write the dissociation equation. But what I'm going to have you do is in the egg puzzle, go ahead and right now I want you to enter just the ions that are produced. So enter those two ions, make sure they have a charge. So what you should have written is sodium acetate is NaC2H3O2. So don't forget, this is a salt. This is not an acid. So you might have gotten lulled into this idea that we are drawing acids, but we are not. So let's just draw these ions. So sodium is 1 plus, acetate is C2H3O2 minus. So there are those ions in solution. When we write the ionization equation, we write this. And why am I writing a full forward arrow? Well, think about our old school solubility rules. This fully ionizes. It has a sodium and acetate are both soluble ions. Okay, so there's that part. Now, just some things. This is what we're doing. And simply you need your calculator. You might need your periodic table, whatever you need to help you. Okay, so we are going to be using our same sodium acetate solution. Okay, so we have this in solution. And what we're going to do, I just might rewrite it a little bit. Okay, so here's our sodium acetate solution, NaC2H3O2 is going to produce Na plus C2H3O2. So down here, I'm going to write, we have sodium ions in solution, we have acetate ions in solution. Hanging out. Now, we're going to pour some acetic acid into this solution. Let's make that orange. So acetic acid is the acid of the acetate ion. Okay, so there's our acetate ion with a proton. Is that one of our 7 strong acids? Tell me. Right? No, it's not a strong acid. It's a weak acid. We're going to be in equilibrium with that hydrogen ion and acetate ion. Okay, so now what we have in solution is now we have some H plus and more C2H3O2. Interesting. Okay, you can see that this is what we have in solution. So when we're talking about this weak acid equilibrium, right, those are the ions we would have. We would also have a fair amount of this. And all of these are in equilibrium with each other, doing things. And recently, we talked about the conjugate of a weak acid acts as a weak base. So this acetate ion is going to go around, it's going to bump into water molecules, it's going to steal a hydrogen off of there sometimes. Things are going to happen. So when we think about the equilibrium going on up here, right, we can imagine sodium doesn't do anything, right? Sodium ion is not the conjugate of anything that affects pH, so we can ignore it. This also fully dissolves, so we can ignore it. So when we think about this system, it's kind of like in Le Chatelier, we added some of this product, okay? And when we think about this, we've put this in, we've dissolved, we've let it come to equilibrium. These are changing back and forth into each other. When we add an acetate, which direction will adding more of this ion shift the equilibrium, left or right? Okay, I hope you said left, right? If we add more product, it will make more reactant. And this actually creates some really cool chemistry. So whenever you have a weak electrolyte and a strong electrolyte, meaning that, that they dissolve, that orange is really orange, um, meaning that they fully dissolve, right? Either a salt or an acid. If you put those together and they have a common ion, that thing that's in equilibrium, that weak thing, will ionize less. Okay, I hope that's making sense. So let's do some pH calculations when a common ion is involved. So we are going to solve for pH. Okay, and ooh, this is interesting. Okay, so we have acetic acid and sodium acetate. So this is what we just did. So we know in that sodium acetate, we can basically ignore the sodium and the sodium acetate that's gone, right? That's fully dissolved. Okay, but what we're interested in is our weak acid equilibrium. So we have our acetic acid in equilibrium with hydrogen ion and our our acetate ion. Okay, so when we look at this problem, our initial amount of our acetic acid is 0.30 mole. Can I put mole in here? No, I can't. I need to put molarity. So how much solution are we making? Oh, we're making 1 liter. So if I put in 0.30 moles in 1 liter, it's just 0.30 molarity. Okay, how much hydrogen ion do we start out with? 0. Yep. How much acetate ion do we start out with? Okay, this is a big deal. We actually started out with 0.30 because we had 0.30 of this to start, 0.30 of this to start, and 0.30 of that to start. The ion to start, before we imagine that the equilibrium has started at all, we have the ion being added from the sodium acetate. Okay, so that's our initial. So this is the big change, is figuring out how to do this. Okay, so change. Now we're kind of just cooking, because this is all the same. Minus x plus x plus x, okay? And equilibrium, well, we can figure this out. This is 0.30 minus x. This is x, and this is 0.30 plus x. You probably want to know what the equilibrium constant is. I didn't give it to you, sorry. The equilibrium constant for this is Ka is equal to 1.8 times 10 to the negative fifth. Okay, and we are again solving for the pH. So let's just write out our equilibrium constant expression just to make sure we're good on it. So we're going to have H plus, we have our acetate ion, all over our our acetic acid. Okay, cool. So let's plug things back in. First of all, can we ignore x here? Heck yeah, we can ignore x. This is small enough. So what we end up getting is, if we ignore x, plus x and minus x, we can't ignore that x, unfortunately, because it's going to be multiplied. We know that hydrogen ion is x, acetate ion is 0.30, and acetic acid is 0.30, and that equals our Ka. Oh, this math actually looks pretty easy, doesn't it? So these are going to cancel. We're going to get that x equals Ka, and look at that, x equals 1.8 times 10 to the negative fifth. Pretty nice. Now, we just need to get the pH. So take the negative log of this, get me a pH, just to practice. Okay, and you should have gotten that it is 4.74. How'd you do? Any questions? How'd that go? We'll do another one. Okay, we'll do another one. It's going to be a little bit different, but we'll get it done here. Okay, and I'll make the image bigger this time. Okay. So I'm going to help you work through making some decisions here. Okay. So as we go, calculate the fluoride ion concentration and pH of a solution that is 0.20 molar NHF and 0.10 molar NHCl. Okay, so here's what we've got. This is interesting. So what I would do is I would just write out the dissociations for both of these. Okay, so we're dealing with some HF, okay, and some HCl. Okay, so strong or weak acid? Ding, 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 strong. So we're not going to worry about this one so much for our pH, right? These just are made. It's all good. Now, the HF, weak. What's our common ion between these two? Yes, exactly. Uh-oh, I shouldn't have used orange, but I did. Okay, hydrogen ion is our common ion here. So what we're going to need to do is we're going to need to set up our good old ice table and help me figure out what to put here. So what's our initial concentration of HF? Yep, it's 0.20. Okay, what's our initial concentration of hydrogen ion? It's 0.10, right? Because this is coming from this dissociation, and we're assuming before this has produced that. So the fluoride ion is going to start out at 0. Okay, what's our change? Well, minus x plus x plus x. So 0.20 minus x, 0.10 plus x, and x. Okay, let's see what the Ka of HF is. So the Ka, let's use green. Ka of HF is equal to 6.8 times 10 to the negative 4. That is small enough that we can ignore x. So this is not looking too shabby. So 6.8 times 10 to the negative fourth is going to equal, okay, so we're going to have our two ions. So we're going to have 0.10, and we get to ignore the x's, 0.10 multiplied by x all over 0.20. Okay, so we just need to solve for x. So when we solve for x, we should get about half, right? 1.4 times 10 to the negative third molar. Now, what is x in this situation? What is x? Let me move my word up, right? X is fluoride ion. Okay, so that means that that is equal to our fluoride ion concentration, which is what the problem is asking us to solve for. Now, we need to get the pH. Our pH is the negative log of our hydrogen ion concentration. Oh, look, the hydrogen ion concentration is 0.1, which means that our pH is equal to 1.00. Okay. Hope that problem's going okay for you. This all works, just to make sure it's really clear, this all works for weak bases as well, which we will try at some point. Okay, let's move on to buffers. So we are going to do some of this together, and I will pause the video. Okay, so let's talk about buffers really quickly, and let's make this nice and big. Okay, so hopefully you have this sheet, and I want you to take a second and read this and click when you're done. Okay, so model one, comparing solutions. So you are going to pause the video again in just a second. And here's what we want you to do. For each beaker in model one, write strong acid, strong base, weak base, conjugate acid, or conjugate base under each molecule or ion in the reaction. Okay, so go ahead and go through these and do that, and then you can check your answers in just a sec. Okay, so one of these two are interacting with each other. One gains a proton, one donates a proton. It doesn't really matter. So I would say weak acid, weak base, right? How do I know they're weak? We've got these double arrows right here, right? And make sure you can see that. Get it to focus in. Okay, so then here, these are both the conjugates, okay? And then this is going to accept a proton, so conjugate base, conjugate acid. Now let's look here. Here, the hydrogen is giving away its proton, so this is an acid. Is it strong or weak? Well, we have a forward arrow, so it appears to be strong. Okay, so this is going to be acting as our base. This is a weak base, right? And so we're making a conjugate acid and a conjugate base here. Okay, and let's just make sure we're connecting these. This is the weak base's conjugate acid. This is the weak acid's conjugate base. Okay, this is the strong acid's conjugate base. This is the weak base's conjugate acid. Okay, now here, HNO2 plus H2O, this loses its hydrogen, so this is an acid. Is it strong or weak? Strong. Water is then acting as a base. Our hydronium ion is our conjugate acid. This is our conjugate base. Again, there are the pairs. Okay, now we have acid here, weak. Here's our weak base. And then we have conjugate acid, conjugate base. Okay, so part two is asking you to do some calculations. You do not need to do all of the calculations. Here's what I want you to do. I want you to do beaker A and beaker D. Okay, so come back in a sec and we will have beaker C done for you. Maybe. Okay, we are back. Maybe that'll go away. Maybe it won't. Okay, we are back though. So what we're seeing here, and I'm sorry, I don't know why I said that was a strong acid. It's a weak acid. Okay, so hopefully you did beaker A. You used KW. Like, oh my gosh, this is just auto-ionization of water. So we have 1 times 10 to the negative seventh of each of these. Okay, here I did this one. So it's a strong acid. So the concentration of the acid before it ionizes is the concentration of its ions. Not a big deal. This is a classic problem like we've done in class. So we just did a weak acid Ka problem. it ended up being, since things are in pretty easy molarities, that the Ka was equal to x squared over 1. So I was able to solve and get 2.1 times 10 to the negative second molarity. Now this harder one is Beaker T. So hopefully you saw that initial for the weak acid was 1 and initial for this ion was also 1 because we added this, and then we need to use our Ka over here from the nitrous acid. Okay, and so down here at the bottom, I got that it was 1, and I got to ignore x because the Ka is small enough. And so I ignored x. I got that the Ka is equal to 1 times x over 1. Now, hopefully you've seen this now twice. When the concentration of your acid and your base, your conjugate acid and base in your equilibrium system are equal, they cancel, and you get that the Ka is equal to the concentration of your hydrogen ion. Hopefully you saw that NO2 minus should just be 1. Okay, so let's look at the back together and let's just talk about these. So here's what we're going to do. We're going to add sodium hydroxide. Acid or base, team? Okay, right? Acid or base. So we're going to add sodium hydroxide. And we're going to see, will it neutralize significant quantities, at least 0.05 moles of it? Okay, or we'll write none. So when we think about this, neutralization is when this hydroxide is going to in some way react with H plus or H3O plus to make water. So let's see. We need to have enough hydrogen ion to react with. So we're going to put, and I should put a minus on that. So we're going to throw some hydroxide ion in here. Is there enough H3O plus to neutralize? No, weak, really weak. There's only 10 in the 10 in the minus 7th here. So no. Let's look here. Is there a lot of hydronium ion here? Yeah, we have a whole mole, or yeah, an entire mole of it in a 1 liter situation. We have a tenth a mole here because we have 100 milliliters. There's plenty of that to neutralize. So yes, okay. The base will neutralize that. How about here? Well, we have some nice things going on. Not only do we have this conjugate acid, we have this original weak acid just hanging out. So when this comes into contact with hydroxide ion, that proton is gone. So this would be a yes. And then beaker D, here we have H3O plus and we have HNO2. So sure. Okay. So our answer would be none, and then yes, yes, yes. Okay, now let's add some hydrochloric acid and see if this will neutralize significant quantities. So for the hydrochloric acid, that needs its H plus to combine with some hydroxide ion hanging out in there or a different base, okay? So let's see what we can find. Is there anything out there that's doing this for us? Okay, so, let's see. Yeah, so anything that can take on this hydrogen ion. So we throw more hydrogen ion in here. Same situation, there isn't enough hydroxide, so no. Throw hydrogen ion in here. There's no, chloride isn't a good base. It's not going to do anything. Okay, so no. Throw some hydrogen ion in here. Now, the NO2 minus could take a hydrogen and become HNO2, nitrous acid again. But is there a lot of that? Look at that Ka. Look at what we said. It's 2.1 times 10 to the minus 2. I don't think so. I don't think that's going to work for us. Now, how about here? We need to do at least 0.05 mole. Here, we have a whole bunch of this conjugate base that will take that H plus. Okay, so no, 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 yes. Okay, so only beaker D. Okay, so what is a buffer? It's a solution that can neutralize both small quantities of acid and small quantities of base. Really cool. We need these. They keep a fairly constant pH. This is how your blood works. Your blood needs to be around an 8 pH. It's a little bit basic, okay? And it needs to stay the same to get all the proteins and enzymes and everything in your blood to keep working. They have to be there. So which beaker in Model 1 contains a buffer? D. Okay. So one way to make a buffer is to mix a weak acid solution with a solution of a salt of its conjugate base. Okay. Why do we need both of them? Well, we need enough of each to react, right? Okay. So let's go down to 8. So I want you to, let's give these a title. And in the ed pause, I want you to read through these and pick which ones you think you would use to make a buffer. Okay. Great. So now you don't need to do 9. And so let's just check these out. How do we think these would work? Well, okay, here is a strong acid. No, doesn't matter. Let's go through. Are there any other strong acids? Yes, H2SO4 is a strong acid, so no. Okay, let's keep looking. Here's a weak acid. That's promising. And then is this its conjugate? No, that's a strong acid. Okay, this is kind of interesting. This puts an H plus in, and this is already an acid, so that one isn't going to work. We need to have the conjugate base. Okay, so not that one. Here we have ammonium, and ammonia. Is ammonium the ion, the conjugate acid of ammonia? Yeah, that actually seems pretty good. Okay, now acetic acid, and then do we have an acetate ion here? Nope. And then we have HF and NAF. They both have the fluoride ion, and that one is good to go. So hopefully you picked C and E. Let me know if you have any questions. Nice job.